Okay, so welcome to Math 355, Lecture 16. So we are starting a new unit today. We are going back to fields, and we're going to be doing algebraic and transcendental numbers. So the big item we're going to be studying, okay, I did change the scale size, which is annoying, but okay. So let L over F be an extension of fields. Let alpha be something in L. We say alpha is algebraic over F if alpha is the root of a non-zero polynomial in f of x. Otherwise, we say alpha is transcendental. So we might take the field to be the rational numbers, and we might look at extensions. We might look at the real numbers. We might look at the complex numbers, and we might ask which real numbers are algebraic, which real numbers are transcendental. And the big question you should always be asking yourself is, who cares? Who cares if a number satisfies a polynomial of finite degree with integer coefficients? Why should that matter? Well, let's try to get a sense of why we might care about some small differences. And so, this lecture is inspired by the fact that we just had the eclipse yesterday. We were within a few hours of totality. So my daughter and I actually drove to Middlebury to see the full thing. And I want to talk a little bit about why small differences matter and why this is worth studying. So you should have already started to read chapter 8. This will give you a little bit more time to finish reading, and you'll hopefully get a sense of why we ask the questions we do, why do we introduce the definitions we do. So here are 3 numbers. Does anybody notice any of these numbers? Can you name them? Yeah, the first one is about the first 125 digits of pi. Second one is less common. How about the third number? I'm sorry? It is not the golden ratio. Golden ratio is around 1.6. If I gave you 1.414, would you know what number that's approximately? That's root 2. You want to guess 1.732? Yeah, so this is actually coming from a beautiful rational approximation to the square root of 3. And so this is just converting that rational approximation to a decimal, but it's incredible how accurate that is. And we'll see a little bit about that later. And so my daughter and I drove 50 minutes last night north to a hotel, and then we drove the rest of the way to Middlebury. We drove on Sunday, then we drove the rest of the distance on Monday. And when we were at the hotel getting ready to check out Monday morning, we heard one of the guests say, "So I can see 96% of the eclipse here. I don't think it's worth driving 90 minutes for just 4%. So the question is, when in life does that 4% matter? If you have an exam and you get 96% or 100%, it's not going to make much of a difference. If you are trying to decide whether or not somebody makes tenure and they have 96% of what they need, tenure is a 0-1 decision. If you're missing that 4%, you don't get tenure. It's a huge difference. And so what you see if you're at totality is completely different than what you see if you are away from that. And so the left is 2 images I just downloaded from the web in terms of, here's almost totality. And then you can see the diamond engagement ring over here beautifully. The ones on the right are the pictures I was trying to take with my dinky camera with the lens over it. It's not bad. You can actually see the moon blocking the sun, and you can see a ring around it. You can see a little bit better over here, just a thin little band coming out. My camera was not really good enough to do a good job, but sometimes those 4% make a huge difference. You can see corona effects. You can see incredible stuff in the second picture that you will not see if you're only at 96%. The second lesson to take away from all of this is that the main term can dwarf lower order terms. So the picture on the left, I took that just a few moments before totality, just before the moon almost completely covered the sun. You can't tell just looking at this with your eyes that you have this moon right in front of it. It's a miracle of distances and ratios that the size of the moon with the distance it is versus the size of the sun and the distances almost perfectly works out so that the moon almost perfectly blocks almost all of the sun. But the sun is so bright that when we're looking at it like this, you can't tell that there's a moon blocking almost all of it. And the other one is just a picture I just downloaded from the web to just get a sense of the moon, coming over and blocking the sun if you put on the filter. And you completely miss this if you don't have the special glasses on. This is a life lesson. Most of you are not going to be working in group theory, abstract algebra later in life, but the lessons that you can get from this are going to be very valuable. And this is what I really want you to take out from this course, is how do you apply these insights in whatever you want to study, be it another field of mathematics, be it finance, consulting, whatever. You frequently have these massive effects that are dwarfing smaller things. And it's the smaller things that really matter. It's the ones that are going to be the movers in the future. And you want to find them. And you need a way to remove those main terms and then extract that smaller, low order behavior that you truly care about. The next lesson is, as always, a picture's worth 1,000 words. So again, I don't know if I can trust this. I found this on the internet. One of my favorite memes is, you can't trust everything you read on the internet, Abraham Lincoln. Right? I regret not buying that sign when I saw it. I should have bought it. So if you look at this, this is a map of the capacity of Airbnbs across America. And while there are some places at capacity that are not along this arc, there is a huge arc across the United States where things are at essentially 100% capacity. Does anybody want to conjecture why that path has such high occupancy? Why do you think there's this path of high occupancy on April 7th, 2024? Yeah, this is basically the path of totality in the United States and a little bit on both sides. It's people trying to get close to totality or be a short drive away from it. And so you can see by looking at this, something is going on. Something is strange here. That's one of the things you want to learn how to do, is when you're looking at data, try to figure out what's worth going on. Now, we also have a lot of other noise. We have a couple of other places throughout the US that are at capacity. But there's this band of 100% occupancy. The last lesson I want you to learn from the eclipse is to adjust to changing times. So it took my daughter and I almost an hour to check into the hotel. And we got there a little bit after 4 o'clock. Check-in is at 4 o'clock. I decided not to mention the name of the hotel. They only had one person available who could help people check in. The other person who normally works the front desk was sick and they couldn't get a replacement. We were lucky. Some of the people behind us easily waited 2 hours, maybe 2.5 hours. Years ago, I was watching the TV show The Apprentice, and one of the challenges they had to do one week is they had to run a fast food restaurant. And one of the team only trained 3 people in how to use the cash registers. Another team made sure everybody had at least some knowledge of all the different skills. And so when a huge crowd arrived, one of the teams could not pull people from the kitchen. It doesn't matter how quickly you cook the food. If the people are frustrated by how long it's taking to order and leave, it doesn't matter. And the first team lost because they couldn't reallocate resources on the fly. This hotel, it was terrible. They could not get a second person to open up another computer to check in. In fact, it was even worse. They finally got a second person to come in to print out the keys for the room to activate them, but she was having trouble. And so the person who was checking everybody in had to then spend time showing the person how to do the keys multiple times. And it was actually less helpful having the person there. It was ridiculous. That hotel had a gift shop. It's closed on Sundays and Mondays. The hotel's at 100% capacity. Open the gift shop. But they just couldn't see to adjust their standard model. They were treating everybody as if it was a normal day, and they had the person, as you were checking in, explaining how to find your room. Well, this slows everything down. They had a bellboy there who could not help people check in, but I said, have the bellboy just give lectures to everybody in line about how to check in. And then you can have the person who's actually manning the computer spend less time. Reallocate. These are lessons that will serve you extremely well in terms of later in life. I also have worked for 6 years in the restaurant industry. If I was in charge of that hotel, I would have had people from the bar, from the restaurant, come to everybody in line and say, we're really sorry for the wait. Why don't we all write down your names and your phone numbers on a piece of paper. We'll call you when it's your turn. Everybody gets a free drink at the bar. And then they might even spend more money at the bar as they're waiting. It's a more pleasant experience than waiting in line. Would have been terrific for the hotel. The image on the right is Yogurt City. And I'm just going to give a big plug to this place in Middlebury. My daughter and I met up with some colleagues of mine. We had lunch at one of the Middlebury dining halls. And then we had about an hour and a half before the eclipse, and we wanted to get some ice cream. And there was a place that was about 1.9 miles away. And I don't mind walking, but I had a really good parking space. And I was afraid that if we moved the car and drive there, then we're going to lose the parking space. And 1.9 miles, doubling that, that's a lot of walking to do before the eclipse. Yogurt City was close. It was only half a mile away, but they're closed on Mondays. But I figured, well, let me just call them just in case the web is wrong. So, oh, yeah, we're open. I said, oh, good, the web said you were closed. Yeah, normally we're closed on Mondays, but with today being the eclipse and all, we thought it might be worthwhile opening. And this was an example of somebody who said, let's adapt, let's adjust to the changing times. So to support them, my daughter and I went to them twice, once before the eclipse and once after the eclipse. So part of it was to support them. The other things, what do you think happened just after totality? What do you think happened after the eclipse was over, after the moon was no longer fully blocking the sun and the sun was starting to emerge? What do you think happened? You have all these people who came to Middlebury to watch the eclipse. What do you think happened? They left. And so you now have a traffic jam of everybody leaving at the same time. So it's like, we can go in the car and we can wait with everybody else, or let's just spend a half hour, we'll have some more ice cream, we'll walk around campus. We actually jogged around campus, and then we'll leave, and then we'll avoid all the traffic and not be frustrated. So again, really think about the different situations. Think about low order terms when they matter. Think about adjusting to the situation. Just because you thought that this is what I wanted to do, well, life throws you curveballs, and it's not always what you expect. And how do I adjust? How do I deal with what I have now? And a lot of places can't adjust, and they are locked in. All right. So what I want to do now is I want to give you a situation where small things matter. So I've done a lot of work with something called Benford's law for a lot of nice data sets. And so I'm the president-elect of the Fibonacci Association. So for me, Fibonacci numbers are a great example. Stock prices, street addresses. What you can do is you can ask, what percent of the time is the first digit of my number 1? So if I give you 2024, the first digit would be a 2. If I give you 0.0037, the first digit would be a 3. And so you might guess maybe 10%, maybe all digits are equally likely, but then you quickly correct from 10% to 11%. Why might you say 11% and not 10% for the first digit? Yeah, we're not going to have 0 unless the number is exactly 0. It turns out for a lot of data sets, the probability of a first digit being 1, 2, 3, etc., it's not all equally likely, but you get 1 about 30% of the time and 9 only about 4.6% of the time. And this is known as Benford's law. So this is a truly wonderful, wonderful result. Not everything in the world follows Benford's law. If you look at batting averages in baseball, if your batting average is below 200, we have a place for you. It's called the minor leagues or retirement. If you can't get a hit 1 out of every 5 times, you're just getting out too often. Maybe if you're a phenomenal catcher, you might still survive and make it, but it's unlikely. Conversely, we don't really have any ball players who do better than a hit 2 out of every 5 times. No one with a lot of at-bats has been able to bat above 400. Most people are clustered between 200 and 400. More like maybe 240 to maybe 330, something like that. And so when you have a lot of clustering like that, I wouldn't necessarily expect all the digits to be equally likely. And I wouldn't expect maybe all the digits to be Benford. There might be some other distribution. But if I have something that's spreading many orders of magnitude, it turns out a lot of the times I will see about 30% 1s and about 4.6% 9s. So here are 4 different data sets. So the first one is the Fibonacci numbers. It's, I think, 30.7%. So it's, it's really good. So it's really good. The next is Twitter users by the number of followers. The next is most common iPhone passcodes. I would prefer not to say how this was obtained. Distances of stars from the Earth. So if you look at these 4 things, you can definitely see there's a lot more low digits as the beginning than high digits. It turns out if you average over lots of different data sets, the fit to Benford becomes even better. So I asked Scott Adams for permission to use this comic strip, which she was kind enough to give me. So a math test indicating fraud is not proof that fraud is happening, but it tells you this might be a place that's worth allocating finite resources. So your travel expenses are rejected because all of your meal costs are round numbers, you're a liar or worse. And then Dilbert responds, I decide what to order based on what totals a round number after 15% tip. You're worse. There is a reason for his behavior. It's not fraud. But when you only have finitely many examples and you're trying to find examples of fraud, if you can have a test that says this is a likely place to look. So there was a major bank that did an internal investigation, and they found in one of their subdivisions of expenditures, there were more numbers beginning with a 4 than Benford's law would predict, and there was reason to believe Benford's law would describe what's going on. They did a little bit more investigation. They saw it was a lot of 4, 8, and 4, 9s. They did a little bit more looking, and it was a lot of 4,800, 4,900s. If you lose a credit card, what do you do? So if you lose your credit card, what should you do? I'm sorry? You notify the company. And so the company immediately puts a hold on the credit card. Now imagine somebody charges $23 worth of gas on your credit card. Is it worth it for the bank to hire somebody to find the $23? To find who stole your credit card? Is the bank going to spend a lot of money to track down $23? No. What if somebody puts in $40,000 of expenditures? Is it worth it for the bank to hire somebody to track down $40,000? Somebody bought a new car in your name. For something like that, yes, the bank will do it. The bank had the critical threshold of $5,000. Anything above $5,000 had to be investigated. Anything below $5,000 could be written off. And what was going on here is there was a worker who was having their friends get credit cards and run up debts just below $5,000. And they would call and they would wait till they got their friend, and then they would report their credit card as stolen. And oh, I'm so sorry to hear your card is stolen. Don't worry about the expenses on it. You're not liable for it. And so Benford's law was able to detect an issue in a situation like this. One solution for something like this is you never tell people that there is something that if you do this, we will not investigate. What you might say is we investigate 100% of anything above $5,000. We maybe investigate 80% of things above $4,000. So everything you have some small possibility. If you've ever been on a plane, what do you have to do if you want to go on a plane? If you want to fly, what do you have to do? You have to do a lot of things. What are the things you have to do if you want to fly on a plane? Buy a ticket. What else? What do you have to do at the airport? What else? You have to go through security. What if we said elderly grandmothers in wheelchairs don't have to go through security? What would you do if you were a terrorist? Let's not answer this because this is being recorded. I'm not going to give advice to terrorists. I believe this as you can't say that there's a certain group that we will not investigate. You might say it might be more advantageous to not investigate all groups equally. This is almost like the Benfords, the biases. But if you say that there's one situation that we're not going to look at, so Benford's law has a lot of interesting applications. It's very useful for analyzing round-off errors. It's useful in determining the optimal way to store numbers. It's terrific at detecting text and image fraud and data integrity. And so a lot of times data fraud, tax fraud has been discovered by people doing these Benford analyses. So this mathematics that I'm going to show you actually has tremendous real-world applications. So a lot of the background material we've already done. So we've done clock arithmetic. So we say A equals B mod C if A minus B is an integer times C. And we're going to basically only care about doing things mod 1 for Benford's law. The significand just comes from writing a number in scientific notation. Hopefully you've seen this in either chemistry or physics. So we can write x as some number, as 10 of x times 10 to the k. K is an integer, and the significand is a number between 1 and 10. So if I give you 2020.1701, I can write that as 2.0201701 times 10 cubed. And the leading digit would be a 2. What's so nice about this is two numbers have the same significand if and only if they have the same leading digits. And if you look at the log of a base 10, we see it's the log of the significand base 10 plus k. But k is a positive, or k is an integer, could be negative. So if I look at this number mod 1, what happens to the k when I look at this mod 1? It goes away. So if I want to study the leading digits of a, I just need to understand the significand. And if I look at the log of 10 of a mod 1, that's the same as studying the log of the significand. Most of the time, you can't just throw away the integer part of your number and then apply functions to it. You can't do that. But here's a situation where you can. And so two numbers have the same leading digits if and only if their logarithms base 10 are the same mod 1. And we're not going to be able to prove results. This would be results for an analysis class. But if you've done some basic Fourier analysis, some basic trig functions, you've hopefully seen Euler's identity. E to the ix is cosine x plus I sine x. Well, if I give you e to the 2 pi I u, every time I increase u by an integer, there's no change because I'm adding an integer multiple of 2 pi. And so this tells you that trig functions are going to be very important in studying Benford's law. So if you've done Taylor series, you've basically seen an infinite dimensional space where my directions are 1, x squared, x cubed. You can also do, instead of those functions, you can use functions coming from sines and cosines and exponentials. And those have a lot of very good properties. They're going to be really well suited for studying Benford. So one of the key ingredients is equidistribution, or evenly distributed, or uniformly distributed. Anything that's important has a lot of words. So we say a sequence is equidistributed mod 1 if the probability that yn lands in some interval ab, which lives inside 0, 1, just converges to b minus a. So what I do is I take some big N and I look at the first big N terms of the sequence. I see how often do I land in the interval ab. I divide by n, and as big N goes to infinity, that should go to b minus a. So if I give you the interval from 1/3 to 2/3, if it's equidistributed, how often should you land between 1/3 and 2/3? 1/3 of the time, 2/3 minus 1/3. So there's a beautiful theorem that can be proved in analysis and number theory, in ergodic theory, that says if beta is irrational, then if I look at the fractional parts of n beta mod 1, that's equidistributed. So whenever you see a theorem, you always want to ask, how important is the condition? How important is it that beta is irrational? Well, let's take a number like 1/5. Let's look at the fractional parts of n beta, where beta is 1/5. I would have 0, 1/5, 2/5, 3/5, 4/5. And what would 5/5 be mod 1? It'd be 0. What would 6/5 be mod 1? It would just be 1/5. It would just cycle. So if I give you a number that's rational, if I look at the multiples, I'm only going to get a finite set. I'm going to keep cycling through them. So if I take any interval that's strictly between 1/5 and 2/5, I would land in it 0% of the time. This might converge to the discrete uniform, but it's not going to converge to the uniform distribution. And so this is a great example where if a number is just a little bit different from a rational number, the behavior is going to be very different in the limit. It might take a while before that kicks in. And if you look at the number, the second number that we started the day with, this number looks very close to a rational. If I truncate it here at the third one, I have a tremendous string of zeros before I get the next one. But this number is not a rational number. There's going to be longer and longer deserts of 0, but there will be infinitely many ones, and it will be irrational. And it will have very different behavior. So I will be explaining where that number comes from. That number actually has a name. It is a Liouville number, and it is a transcendental number. We will talk about why it's transcendental later. It is a good question to ask as to where it came from. It is not an arbitrary number. It was chosen because it's easy to analyze. So I chose the square root of pi as a good number to look at. And so square root of pi is irrational. So if I look at n root pi mod 1, that should be equidistributed. So I'm looking at the first 10 data points. And I'm looking at how often am I in the different intervals of length 1/10. So 0 to 0.1, 0.1 to 0.2. I see 8 out of 10 times I land in the interval once. One time I land in 0, and one time I land in twice. Do you think this is reasonable for 10 data points? That's not bad for 10 data points. What can you do, though, to get more confidence? Yeah, add more data. And so you should, if you haven't taken a stats class, you should take a stats class before you graduate so you can get a sense of, are these good fits or not? So here's 100 data points. And you can see now that the fluctuations are much smaller. Everything is more than 0.8, nothing is larger than 1.2. We can take even more data. And if I look at the first 1,000 points, it's becoming tighter. I can look at the first 10,000, and it's becoming extremely tight. You can see small little fluctuation, but it is converging. A big question for the subject is how quickly does it converge? And this is going to depend on the algebraic structure of your irrational number. And there are ways to quantify how irrational is a number. So the fundamental equivalence for Benfords is that a data set xi is Benford, so it has this digit bias if and only if the logs mod 1 are equidistributed. So let's think about what's going on. So if I write my number as significant times 10 to the k, what's the log base 10 of 1? So the log base 10 of 1 is 0, and the log base 10 of 10 is 1. So the significand lives between 1 and 10. Its logarithm is going to live between 0 and 1. So if I want a first digit of 1, the significand has to live between 1 and 2. The log of 1 is 0. The log of 2 base 10 is 0.3 roughly. That's why 30% of numbers have a first digit of 1. What's going on is this digit bias you're seeing in Benford, it's coming because you're looking at numbers the wrong way. You shouldn't be focusing on their first digits. You should be focusing on the log of the significance. And so just writing it vertically, if I want to calculate what's the probability of a leading digit of d, well, I would have to be all the numbers from d to d plus 1. So I would get the log base 10 of d plus 1 minus the log base 10 of d. And when you subtract, that's the log base 10 of d plus 1 over d. And then you can just use properties of logarithms. The log of a quotient is the difference of the logs to show that this sums to 1. So probability distribution, the probabilities have to be non-negative and they have to sum to 1. So the main lesson here is the need to look at things from the right perspective. So I love Rubik's Cubes. The second Rubik's Cube is one of my favorite. If you look at it, it's got sides that are 2 by 3. You shouldn't have a side that's 2 by 3. The sides are supposed to be 3 by 3. It looks very different. It turns out these cubes are isomorphic. And so we've talked about isomorphisms between groups. Here's an isomorphism between cubes. A lot of things in life try to mislead you, such as my exams. I might put on some information that's not relevant. Well, the real world is like that, where you're often thrown things that have absolutely nothing to do with the problem you're studying. And a key part of your job is to figure out which things really matter. When you're doing research, you have to figure out which things really matter. Now, one of the problems when you're doing research is you may not have all the tools that you need. On an exam, I will always make sure you at least have all the information you need to solve the problem. I might give you more information than you need, but you'll at least have all the information you need. It turns out if I hold this cube at a 30-degree angle and spin it like this, then you see 3 blues, 3 reds, 3 reds. It's really a side. But it's presented in such a way that it doesn't look like a standard cube. Now, there is a slight difference you have to be careful about. In the standard Rubik's Cube, if the center is rotated by 90 degrees, you can't tell because everything is a solid color. If you put an image on the cube, you can now tell if the center is rotated. And so it turns out that this cube is not quite the same as this cube. The two cubes are not the same, but they are the same if the standard 3 by 3 by 3 cube has pictures on the sides. So it's the same as I have to make sure that when I solve it with the centers in the right orientation. Okay, so some exercises. You should prove that that the log of 2 base 10 is irrational. That's a nice exercise. So if you prove that, then you would get 2 to the n is Benford base 10, because if I take the log of 2 to the n, I get n the log of 2 base 10, and we're assuming that the log of 2 base 10 is irrational. So you should prove that. The next is that the Fibonacci numbers are Benford. And so this is a beautiful argument. And so the Fibonacci relation is Fn plus 1 is Fn plus Fn minus 1. They usually start 0, 1, 1, 2, 3. So the Fibonacci numbers are increasing. So because the Fibonacci numbers are increasing, does everyone agree that Fn plus 1 is going to be less than or equal to twice Fn? Because Fn is going to be greater than Fn minus 1. So if I replace Fn minus 1 with Fn, I've only made the right side larger. So this implies that Fn is growing slower than 2 to the n. I'm not doubling, eventually. With a little bit more work, you can show Fn plus 1 is greater than or equal to 2 Fn minus 1. And that will give you that Fn is growing faster than the square root of 2 to the n. So again, it's a nice exercise. Try to prove something like that. What this means is I'm growing slower than 2 to the n. I'm growing faster than root 2 to the n. Maybe I'm growing at the speed of r to the n for some r. This is not a proof, but it says this might be something worth trying. So one of the things you need to learn if you're going to be a professional mathematician is, can you do these kind of, quick heuristic arguments to get a sense of what might be worth studying? Well, if I guess Fn equals r to the n, I plug this into the recurrence relation and I get r to the n plus 1 is r to the n plus r to the n minus 1. So I divide both sides by r to the n minus 1 and I get r squared equals r plus 1. What do I have to be careful about if I divide both sides by r to the n minus 1? Division by 0. Well, if r equals 0, then I basically get all the terms as 0. That is a solution to the Fibonacci recurrence, but it's a boring one, and it's not going to work with the initial terms being defined as 0, 1, 1, 2, 3. So I don't really have to worry about that. So I find the roots of this quadratic, and I get r is 1 plus or minus root 5 over 2. And now, hopefully you've seen stuff like this in linear algebra. If r to the n is a solution, if I multiply it by any constant, that's a solution. And if I sum two solutions, it's a solution. So if I call the two roots r1 and r2, we get the general solution is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. So 1 plus root 5 over 2, this is larger than 1 in absolute value. So this term is going to be exploding. What about the 1 minus root 5 over 2? What can you tell me about its size and absolute value? So can you tell me how big is the root 5 approximately? A little bit over 2. So it's definitely greater than 2. It's less than 3. So if it was 2, I would get negative a half. If it was 3, I would get negative 1. So 1 minus root 5 over 2 is less than 1 in absolute value. So as n gets really, really large, the second term doesn't really matter. So the nth Fibonacci number, when n is very large, is approximately 1 over root 5 phi to the n, where phi is the golden mean. So the log base 10 of Fn is approximately n log base 10 of phi minus 1/2 log 5 base 10. So when I'm looking at the log of the Fibonacci numbers mod 1, the minus 1/2 log 5, that's just a constant shift. It's not going to really affect if it's equidistributed or not. If the log base 10 of the golden mean is irrational, which I strongly urge you to prove, then this tells me that the Fibonacci number should be Benford. So assuming this theorem from analysis or number theory, which we sadly will not be able to prove, this suggests that the Fibonacci numbers are going to be Benford. A lot of things in the real world are described by recurrence relations. This is one reason why so many things are Benford. Not every recurrence is Benford. I've given you an example here of a recurrence relation that's not Benford. Going back to the Benford probabilities. If you think about what's going on, imagine you have a really nice stock market that grows at 2% a year every year. To get from 10,000 to 100,000, I'm sorry, to get from 10,000 to 20,000 to change your first digit, you have to double your value. You have to increase by 100%. So it's going to take you a while to do that if you're only growing by 2% a year. But to get from 90,000 to 100,000 to change the first digit at the end, you only have to increase by 10,000 out of 90,000. That's only 11% versus 100%. You spend a lot more time with a leading digit of 1 than you do with a leading digit of 9. And so this gives you some sense that if you have these geometric processes, you expect to see Benford behavior. And really, what we have over here, 2 to the n, this is just the recurrence relation. An plus 1 is twice an. And that will have solutions 2 to the n. So if you have a fixed growth rate, that's going to be a nice recurrence relation, and we do expect Benford behavior. So let's look at the first 60 values of 2 to the n. And so I've said that the log of 2 base 10 is irrational, so that this should be Benford. So the numbers start to get quite large, so I'm only going to display the first 30 numbers. And then I'll look and see how often do I have a first digit of 1, 2, 3, and so on. I'll look at the observed probability, and I'll compare that to the Benford probability. So for the first 60 values, 18 of the values of the first digit of 2 to the n is a 1. So that's a 30% of 0.300 probability. Benford is 0.301. That's a pretty good fit. What about looking later on? Do you think that this is always a good fit, or do you think the Benford probabilities might have some issues with some places? Well, actually, I'm doing 60 values. I'm only displaying 30. I only have 60 values, and you should be very hesitant about making claims with 60 values. Do any of the data here look particularly bad? Well, I would agree with you, and that's the one I highlighted. I would say the 9 is the worst. But again, it's only 60 values. So before the Red Sox came back down 3-0 against the Yankees in 2004, they were the first baseball team ever to do this. No baseball team had ever done this in a best of 7. So in a best of 7 playoff series, whichever team wins 4 games first advances, the other team goes home. There'd been like maybe 24 times that a team had been down 3-0 and the team had never come back before the Red Sox. Why do you think a team might never come back? You're down 3-0. If the two teams are equally likely to win a game, what should be your probability of coming back if you're down by 3 games? You have to win 4 games in a row. So if you win each game with probability 1/2, what's the probability? 1/16. So if it's only happened on the order of 24 times, you would only expect once, maybe twice a team to come back. Well, if it's happened 0 times, that's not so unlikely. It's small data. Why else, however, might a team not come back if you're down 3-0? You could have a mental block, but there could be a reason why you're down 3-0. Why might you be down 3-0? I like the Williams baseball team, but imagine the Williams baseball team is playing a Major League ball team and they're down 3-0. What do you think the chance of the Williams baseball team of coming back? Not good. And since I'm the faculty advisor, I'll leave it as not good. I love the Williams baseball team, but if they're playing a Major League team, why do you think they would have basically no chance of coming back down 3-0? Why might they be down 3-0 against a Major League team? I don't want to say the Williams baseball team is bad. Say instead that the team they're playing is just much better. If you're down 3-0, one of the reasons you might be down 3-0 is that the other team is just better. So if we said, all things being equal, you have a 1 in 16 chance of coming back, and we're a little bit surprised that no one has ever come back, well, maybe no one has ever come back because you're down 3-0 because you're not as good of a team. So you'd want to have more data as to the two teams that were playing. Are they of similar ability, or is one team much better? Is that why they're up 3-0? So you always want to be careful about interpreting data. Frequently, you want to have at least 5% of your observations in each bin. And for the last 1 or 2, these are really close to the 5%. If we combine 8 and 9 into a little bit larger bin, then the probability would become 0.097, and the observed value would be 0.100. That's an almost perfect fit. So we might just be using too many bins, and it might be looking bad because we're trying to look at too many digits and we don't have enough data with just 60 observations. Does anybody know how many megabytes are in a gigabyte? If you know your classical languages and your prefixes, how much should it be to go from mega to giga? It should be a factor of 1,000. But in computer science, it's not a factor of 1,000. It's actually 1,024. And as you're downloading a file, you could be at 994, 995, 996 megabytes. And then when you hit 1,000 megabytes, you don't hit a gigabyte. It's like 0.99 gigabytes. And the reason is 2 to the 10 is 1,024. And computers work base 2. So it's much better for the computer to have 1,024. We'll call that the correct factor. Now, if 2 to the 10 actually equals 10 cubed, then the log of 2 base 10 would be 3/10. And the log of 2 base 10 would be a rational number. It's not a rational number. It just misses. It's 1,024. And that extra 2.4%, that's what leads to the Benford law. If you look at what's going on, these numbers are particularly chosen. Every time we increase n by 10, it's almost the same as just putting in 3 zeros. That's why we almost go from 1 to 1,000 to 1,000,000. If it was, then there would be no Benford's law. It's going to be a long time before we finally see a first digit of a 7 or a first digit of a 9. Those will occur, and eventually we will get the Benford probabilities. A big issue for the Internal Revenue Service and other people who are looking to detect fraud is how much data do you need before you can be sure that something nefarious is going on or that it's worth investigating further? How quickly should Benford be converging? This depends on fine structures of the numbers. So why are we spending so much time discussing, is a number algebraic, is it transcendental, what kind of polynomial does it solve? That information has a lot of applications for number theory, for abstract algebra, for mathematics. Okay. So the next is, how many of you have done some basic statistics, goodness of fit tests? Have you seen this? So this is the 21st century. If you haven't taken a stats class, you should remedy that before you graduate. You need to know how to do some basic data analysis. It's a very useful skill to have. And so here, the chi-squared value is a measure of how much you deviate from the theoretical prediction. The smaller the value, the more likely it is that the theory is describing reality. And so if Benford's law is a good fit, then I really, 95% of the time, I should get a chi-squared value of 15.5 or lower. The smaller the value, the better the fit. And I chose 3 irrational numbers. I chose pi because everybody loves pi. I chose e, everybody loves e. And I chose gamma because gamma is not quite as well known. And so whenever I get a chance to plug it, I'll plug it. And so gamma, if you've done the integral test in calculus, the harmonic series diverges. If you sum all the integers up to x of 1 over n, it's about log of x. How much does it differ from log of x? That's where gamma comes in as the first low order term of the difference. And so what do you notice when you look at these chi-squared values? So you want to get to the point where you can look at data and make some predictions. So what do you notice when you look at this? So what do you see? Which numbers look good? Which numbers look bad? Do any of these numbers look like their chi-squared values are consistently below 15.5? That's just the critical threshold that if your theoretical prediction is correct, then 95% of the time your value should be 15.5 or less. The smaller it is, the less deviation. It's a way of measuring how far you are from theory. So the larger the number is, the less likely it is that your theory is describing what you're seeing. So which numbers look like theory Benford is describing what happens when we look at their first digits? Gamma and E. Do the chi-squared values consistently get smaller? Almost. So it's getting smaller, 0.72, 0.24, 0.14, 0.08. Then it goes up to 0.19, then 0.04, then 0.09. So it's actually oscillating a bit, but it's pretty small. The values for E, again, it's oscillating. It looks like it's going down, but then it goes up. The values for pi are a lot more interesting. They start off quite large, they get small, and they get actually modest again at 6.19. It's still smaller than 15, so other than that first value, it's pretty good, but it's definitely a lot larger than the others. So the powers of pi are not being as well fit by Benford as the powers of E and the powers of gamma. Can anybody give me the first few digits of pi? Three. Okay, 3.1415. Okay, good. You've got to know at least 3.14159 if you want to be a math major. What about powers of pi squared? Did you ever memorize those? Can you at least give me the first digit of pi squared? 9. All right, so like the gravitational constant? 9.8 meters per second squared. Well, 3.1 times 3.1 is 3 plus 0.1 squared, so it's 9 plus 0.2 plus 0.01, so it's about 9.21. But it's really 3.15, so it's going to be a little bit less than G. Pi squared is not too far off from 10, which can cause some problems in terms of orders of magnitude. So when I look at this data, one of the things that's really annoying is I have something of size 46.65 and something of size 0.02. That's a lot of orders of magnitude difference between them. Did either of you feel the earthquake a couple of days ago? So my daughter was home, and so she and I felt the earthquake. We were wondering, the wind should not be shaking the house this badly. We felt it. Now the earthquake was, I think, around like a 4.5 centimeters in New Jersey. There was an earthquake in Taiwan a few days earlier that was, I think, around a 7.5. The earthquakes are measured on a Richter scale, where every time you increase by 1, that's an order of magnitude. And so the one in Taiwan was 3 orders of magnitude, about 1,000 times worse than the one that hit New Jersey. Completely different impact of what that is. It's very difficult to talk about things that vary so greatly in terms of order of magnitude. And so you need a good way to display things. So when you did logarithms in school, did they ever tell you why we care about logarithms in school? That's a sad question, but a valid one. So most of the time it's like, we are doing math to do math. We are doing physics to do physics. This is why I wanted to spend today motivating why are we going to talk about algebraic versus transcendental numbers? Why do we care? Who gives a damn question? You should be asking this. And if you're not asking this, then someone else should be hopefully answering it for you. And so the problem is we have a lot of material that needs to be covered, and we don't always explain to people why we are covering it. And so logarithms have 2 great uses. One use is they allow us to talk about sums. So the log of a product is the sum of the logs. We have a lot of understanding about how to deal with sums. Another reason we care about logarithms is they allow us to talk about things that span tremendous orders of magnitude on the same scale. You want to talk about something subatomic and something of galactic size, we can do that. And so what I'm going to do is I'm going to plot the chi-squared values, but I'm going to plot them on a log scale. And so I'll just plot pi and e. Gamma is not quite as popular. And so what can you tell me about the plot? So the red is the first digits of pi to the n. The blue is the first digits of e to the n. So when you look at the blue, does that seem to be generally going down? Yeah, and it's around negative 1.5, negative 1. So that would be, a small value. Okay, that's going to be a good chi-squared fit. What about the red? What about the plot of the chi-squared values for pi to the n? What do you notice about these red plots? So what do you notice in the patterns of reds? You're data scientists right now. What do you notice? I want you to be making conjectures. Describe the red. Just use qualitative terms right now. What do you see? It's like what?
Like a bunny hopping.
It's like a bunny hopping. Okay. Is the bunny hopping the same way, or is the bunny doing different steps? Okay, the width, it looks roughly the same. What about the structure? Does the structure look the same? Yeah, the structure looks mostly the same. What would you estimate the width to be? I can zoom in a little bit if that helps. What might you estimate the width as? Less than 200. Can you be a little bit more specific than less than 200? Do you want to do 160 or 170? So how much is each tick? 50. So the third tick here is 150. The fourth one here is 200. What would you estimate that at? 175. All right. So 175 is a reasonable estimate. So, I just want to be a little bit careful. Two of my friends actually took a year off from college to help a magician set up his institute to debunk people who claim to have psychic powers. Right. So I just wanted, for the record, that you chose 175. So we talked about powers of pi. We talked about pi squared. I'm assuming no one has ever calculated pi to the 175. But if you did, you would notice that pi to the 175 is approximately 1.0028 times 10 to the 87. So pi to the 175 is almost 10 to the 87. If it was 10 to the 87, then every time we increase the exponent by 175, we would return to where we started, just padding it with 87 zeros. Because it's not, this means that it will eventually become Benford. But it's going to become Benford at a very different rate than 2 to the n. 2 to the n was about 1.02. That was about 2.4%. And that was only taking an exponent up of size 10. Here, if we go 87, we go 175 times, it's an order of magnitude less in terms of the difference. But that small difference is going to make a huge, going to have a huge, huge impact later on. And this is one of the reasons why we care so much about the structure of a number, because different types of numbers will have very different behaviors. All right, so now it's time to switch and start talking about some of the key concepts we're going to be looking at. So have either of you ever heard of the Hilbert Hotel? Okay, so we'll do this part a little quickly then, because I know we do have people in Zoom today. Every room is booked, but we can always take more people. This is not like the hotels I stayed at yesterday or dealing with the eclipse. Those were definitely at capacity and they could not take more people. I actually heard that the New York Highway Patrol was fining people $250 if they caught you sleeping in your car on the highways. I don't know if one fine would be good for the entire night or if they could fine you multiple times, but some Airbnbs were charging thousands of dollars in totality and said, hey, we have a room available tonight if you want to come. So the question is, you have every room booked. There's infinitely many rooms in the hotel, and a guest shows up. How can we find space for the new guest? Shift everyone down. Guest arrives. Shift all down by 1. So 1 goes to 2, 2 goes to 3, 3 goes to 4, ... Frees up room 1. If we had 6 people arrive, where should we shift 1 to? 7. So we can actually deal with any finite number. So any finite number n is trivial. 1 goes to n plus 1, 2 goes to n plus 2, ... What if infinitely many arrive? What can we do? Excellent. So you send everybody to the double. So 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. Oops, go the wrong way. ... Frees up rooms 1, 3, 5, 7. So we can actually free up infinitely many rooms. And what's going on here is this is kind of strange, but we can have 2 sets with infinitely many elements where one set is a proper subset of the other, but they have the same size in some sense. What do I mean by the same size? So we say A and B and D have the same size if there exists a one-to-one onto map F from A to B. And of course, as soon as I say that there's a one-to-one onto map F from A to B, then F inverse exists and is the map from B to A. So we will say 2 sets are of the same size if I can put them into one-to-one correspondence with them. And so if I add 1 to a nice finite number of people, it's trivial. Even if I add infinitely many people, we can still handle it. So this leads to the notion of a set is countable if it can be put into a one-to-one correspondence with the integers, or equivalently with the negative numbers. So let's say I give you the integers. So ... -2, -1, 0, 1, 2, ... I want to put this into a one-to-one correspondence with the integers. So I'm going to send 0 to 0. Any ideas what I should send 1 and 2 to? Yep. 2 to 1, which should I send 1 to? I'm sorry? It just makes doesn't really make much of a difference. I think it makes the form a little bit cleaner. What should I send 1 to? So 0 goes to 0. I've got to get all the positives. I've got to get all the negatives. I'm going to send 2 to 1. What number do you think I should now also take care of? Negative. I've got to do 3 and 4. I'll send 4 to 2. Where do you think I should send 3 to? Negative 2. And so I get the nice formula, f of n, the f of 2n is going to be n, and f of 2n minus 1 is going to be negative n. That's why I wanted to send 2 to 1. So now the definition of 0 actually falls the same way. And so here's a nice one-to-one correspondence between the integers and the non-negative integers. If we have a countable set, we'll often write A as, A0, A1, A2, ... Or maybe we'll do it as, A1, A2, A3, ... Sometimes we start indexing at 0, sometimes we start indexing at 1. It doesn't really make much of a difference. All right, so a countable set is basically something of the same level infinity as the integers. And the natural question is, do all sets have the same infinity? can you have different levels of infinity? And we will see that the answer is yes. So it turns out the rationals are countable, and more generally, a countable union of countable sets is countable. And so let's imagine, each AI is countable. And let's let A be the union I equals 1 to infinity of AI. And maybe we'll write each AI as AI1, AI2, AI3, dot, 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 dot. And so what we want to do is we want to show that if we have a countable union of countable sets, that this is countable. So proof. So I'm going to write the sets as follows. I'm going to write A11, A21, A31, A41, dot, dot, dot. A12, A22, A32, A42, and so on, so on, so on. A21, oh, sorry. A13, A23, A33, A43, and so on. And then I might want to start counting not at 1, but counting at 0. So if I want to start counting at 0, I would have an A01, an A02, an A03, and so on. And maybe I have a 0 row down here, so A00, A0, sorry, A10, A20, A30, A40. So you have some freedom in terms of how you want to do things. So what I want to do is I want to show you, you give me any element in any set, and I will tell you when I get to it. And so there are two methods that are usually done. One is the diagonal lines. And I draw each line along a diagonal like this. So the first one has 1 element, then 2 elements, then 3 elements, then 4 elements, and so on and so on and so on. And if I draw it like this, you can tell me exactly when you will get to any specific element. You want to know when do I get to the 2000th element in the 53rd set? I can tell you exactly which diagonal that is. The other method people like to do is they like to use the square approach. I first do A00, then I just keep doing larger and larger squares. Go up to the diagonal and then over. Have you seen these arguments before? Have they normally done diagonals, or have they done the rectangular? Normally diagonals, yeah. Both of them are fine. And so this gives me a nice way. So this actually proves that the rationals are countable. And so for the rationals, this is all numbers of the form A over B. B does not equal 0. A and B are integers. Without loss of generality, enough to show that the positive rationals union 0 is countable. Or just that the positive rationals are countable, because I can either easily add 0 and then I can easily add the negatives. So there's a nice one-to-one, there's a nice correspondence. If I give you a rational A over B, I can associate that to the pair A comma B. And so what I'm going to do is I'm going to just write all the numbers. So I'm going to write, I'll start doing it as 0, 1, 1, 1, 2, 1, 3, 1, dot, dot, dot. And then I'll do 0, 2, 1, 2, 2, 2, 3, 2, dot, dot, dot. 0, 3, 1, 3, 2, 3, 3, 3, and so on and so on. So what number does 0, 1 correspond to? Which is 0. And what does 1, 1 correspond to? 1, and then 2, and then 3. 0, 2 would also correspond to 0. 1, 2 would be 1/2. 2, 2 would be 1 again. 3, 2 would be 3/2. Then I would have 0. I would have 1/3, 2/3, and 1. And then what I can do is, do you want to do diagonal, or do you want to do square? I don't care either. No, there's many ways. Some people do the snake approach. You could do something like this. That's going to be harder to write. But if you want to do the snake approach, I'll do the snake approach, you know. Sure. So let's write down the numbers as we go, but only write the number down if it hasn't been done before. So we'll have 0, 1, 1/2. We don't write down 0 because we already have 0. We don't write 0 because we already have 0. We would then write down 1/3 because that's new. We would write down 2/3 because that's new. We don't write 1, we write 2 because that's new. We write 3 because that's new. We write 3/2 because that's new. We don't write 1 because that's not new. And this shows you that I can snake through and get every rational number. And I just write down which number. Now, if I truly, truly hated you, I would give you an exam question saying, you know, write down the explicit formula to find when you first hit the rational m over n. And that could be an interesting question to see how does that depend on the way you write things. No one would want to do this. This is a great example of you don't make it explicit. You just know that there is a way to do this. The rationals are countable. Now, continuing, it turns out that the reals are uncountable. So I'm going to just sketch the proof by Cantor. So it's enough to show that the real numbers in 0, 1 are uncountable. Because if they were countable, then the reals between 1 and 2 would be countable, and between 2 and 3 would be countable, and the union of countable is countable. So I just have to show that the reals in 0, 1 are uncountable. So assume not. Write each xi in decimal. And we are assuming that they are countable. So I can write that as the union of xi, I goes from 1 to infinity. So that's the assumption. We're going to assume that the reals in 0, 1 are countable. Now we have a problem. And that's why this is just a sketch. The number 0.019999 repeating is the same as what number? 0.02. So one option is maybe look at both representations. Or choose one. I'll let you figure out how to deal with this. So if I write my numbers x1, x2, x3, dot, 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 this is point x11, x12, x13. This is point x21, x22, x23, dot, dot, dot. This is point x31, x32, x33, dot, dot, dot. And now what I'll do is I go along the diagonal and I form a new number x, where the kth digit is 9 minus the kth digit of xk. So note, x and xk differ in the kth digit. Can they be the same? So is it possible that two numbers could differ in the kth digit and be the same? Yeah, we have this damn problem, that's a technical term, of 0.01999999 is the same as 0.02. So make this rigorous. So make rigorous. Maybe work in binary. Maybe remove all numbers with two expansions. And so maybe all the numbers that have two expansions, maybe there's only countably many of them and I can remove them. So I'll leave this as an exercise for you as to how do you make this rigorous. This is not a class in set theory. This is hopefully enough to see, okay, I can see roughly how you can do an argument like this and show that the reals are uncountable. Why is this interesting? Well, we have a beautiful theorem now. The set of algebraic numbers is countable. So proof So let's let an be the set of all alpha. Alpha is a root of a polynomial of degree n with integer coefficients. So if you have a polynomial of degree n, so if f of x is a polynomial of degree n, how many coefficients does f of x have? N plus 1. So given any f, I can associate a 0, a 1, dot, dot, dot. No. I'll do it a 0 of f, a 1 of f, dot, 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 a n of f. So each f I can associate, it's coming from n plus 1 numbers. How many choices do I have for a0? A0 is an integer. How many choices are there? Countably many. So this is countable, cross-countable. So this is, the union of countable sets, right? I can view this as living in an n plus 1 dimensional space. I can use the grid I did before. What can you tell me about the number of such polynomials? How many are there of degree n? Countably many. So countably many f of degree n with integer coefficients. How many roots can one of these polynomials have? At most n. Each at most n. So the roots of polynomials of degree n with integer coefficients is countable. So each an is countable. So a union is countable. As the reals are uncountable, we see that almost all reals are transcendental. And this is in a very interesting position. We have now proved that almost every real number is not the root of a polynomial with integer coefficients of finite degree. Can somebody give me a transcendental number? We don't have much time. Yes. And can you prove it? No. The proof is actually not that bad. It's a lot of tedious algebra, but it's not that bad. Let's go back to the very beginning of the lecture. Foreshadowing. Anybody want to make a guess about the second number? Yeah, this is actually related to the sum of 10 to the negative n factorial. What kind of number do you think it is? It's transcendental. So this is called a Liouville number. These are the easiest numbers to show that it's transcendental. I can actually show that that's transcendental in abstract algebra. E and pi I could show, but it would be a lot more painful integrals to do. All right, it is 11:10. We got the lecture done in the allotted time. We did a lot today, a lot of life lessons from the Eclipse in totality. And this is a very good place to stop.